In the following slides, we will describe the overview of content-based image retrieval. Content-based image retrieval, abbreviated as CBIR, is one of the most important research fields in the multimedia content analysis. And in the following, we will briefly give you an introduction about CBIR. And the teaching material is mainly from this paper. This paper was published in Journal of Visual Communications and Image Representation, 1999. And the authors of these papers are quite famous. The first one is Ray Yong. Okay, now he is working for Microsoft China. And the second one is one of the pioneer of the computer vision image processing field, and he is actually from Taiwan. He is Professor Thomas Huang, and now he is in University of Illinois, Urbana-Champaign. Another one is also from Taiwan, Professor Shifu Chang. He is working at Columbia University, and he is also one of the pioneers in multimedia content analysis. And in this paper, they describe the image retrieval, the current techniques, promising direction, and the open issues at the time of 1999. Image retrieval has been an active research field since 1970s, with the demands from the research community of database management and computer vision. Because from that time, there has been some database management system, and the people are getting used to search text-based data from the database. And so people were wondering whether we can, as a user, if we can search images from the database as well. And the computer vision research field just emerged at that time. So there are more and more people realizing the demands of image retrieval. And at the first, some text-based approach has been proposed because it originated from the database management system. And in the text-based approach, they first hire user to annotate images by text, and then they store this text data at the database management system. And actually, when they do image retrieval, they don't really perform image retrieval. They do text-based image retrieval. And when relevant texts are retrieved, then the corresponding image are then retrieved. So this is the approach for image retrieval at the very early time. And in the early 1990s, two difficulties arrived largely because starting from 1990s, more and more digitized images can be produced and stored and share with others. And according to the emergence of internet, there are much more digital images available on the internet. So hiring users to annotate images become an invisible task. So this amounts of labors required to annotate large-scale image collection that would not be possible. And the rich content in the image and the subjectivity of human perception also cause a challenge. The subjectivity means for the same photo, for the same image, different people may have different perception or different interpretation on this image, so that different people may annotate the same image in different ways, and that causes a problem. So starting from early 1990s, instead of annotating by text-based keyword, images are indexed by their own visual content, such as color and texture. So the idea of content-based image retrieval emerged starting from early 1990s because researchers want to describe image by visual content rather than text-based information. And here is a general architecture for an image retrieval system. So given an image collection, we may need to extract features from the images. And because if we represent image pixel by pixel, that would cost a lot. So we need to extract representative features, or we have to do some signal processing to extract representative information from the larger amount of images. So we have to do feature extraction, and then we will compare the visual features between images so that we can know the similarity between different images. And of course, if we have time, we can hire people to do text annotation. Okay, so a user may give a query through the query interface, and the so-called query in content-based image retrieval system, the so-called query may be another image, and then we also have to extract features from the query images, and then we will compare we will calculate the similarity between the query image and the image in the database. And there may be some multi-dimensional indexing techniques applied to do retrieval more efficiently. Okay, and this is the whole architecture, and basically different components are associated with different technologies. For example, to have a large-scale image collection, we may need image processing technology and image compression technology. And for feature extraction, we may need computer vision and image understanding technologies. For text annotation, we can acquire technology from information retrieval or database management system. To more efficiently index or search high-dimensional data, we may need computational geometry, database management technology, and the pattern recognition technology. And to process the query, we may need database management technology. And to design a better query interface, we may need to study user psychology and user interface. So the whole image retrieval system uh, consists of many components, and that should be associated with many technologies. Let's look at one of the typical uh, example research about CBIR. We will introduce the VisualSEEK system. The VisualSEEK system was published in 1999 at ACM Multimedia, and you can see the author. One of the authors is Professor Shifu Chang, and this is another famous researcher, J.R. Smith. Now he is working for IBM Research. And although this system was published 20 years ago, there are some important concepts we can study when we want to study our own content-based image retrieval system. Okay, so in the early time, in this work, they try to enable query by image regions and spatial layout. And basically, the CBIR research emerged around 1994 or 1995. I still remember there is a pioneering CBIR system called QBIC. developed by IBM. And at that time, we can query, we can give a image query by sending the whole image so that a similar image to this query image can be retrieved. And at the VisualSEEK system, they try to more finely uh, do the image query. So they try to enable query by image regions, not only the whole image, but also the image regions. And they also try to consider the spatial layout of these image regions so that we can do more accurately content-based image retrieval. Okay, so the target is they try to enable unconstrained images that will be decomposed into near symbolic images, which lend to efficient spatial query. So not only the visual content, color or texture, they also try to consider spatial relationship, and they will address spatial query involving adjacency, overlap, or encapsulation of regions. So here is an example. A query image may be like this. We can draw a figure, or we can draw a people here, and draw a car here, and assign the color uh, of these two objects. And we can also assign the spatial relationship between these two objects. For example, the people may standing on the left, and the car may be located on the bottom right. And here is the maybe the example target images. If we don't care the exact spatial location, we just find uh, the images have um, that have people in red and color and the car in pink, so that this image can be retrieved. Okay, so here is the uh, detailed information about these images. We may be able to detect the objects and their location, as well as their spatial properties. So this is the goal of this system. So to achieve this goal, they need to devise an image similarity function which contains both color information as well as the spatial component. So this would be the major contribution of this paper. And at that time, and 20 years ago, this concept is quite uh, pioneering. Okay, so we will discover some intrinsic parameters like the similarity between query and the target color, or region size, or spatial location. And we also have some derived parameters, like the inference that can be made from the intrinsic parameter is called the derived parameters, such as the relative spatial location and the overall assessment of image match with multiple regions. So when we detect object, we may just realize the absolute location of these objects, but we can derive their relative spatial location between different objects. Okay, so these are called the derived parameters. So here is the concept. We may give a query like this. Okay, we may assign there will be a red circle, a green rectangle, or a blue polygon. Okay, and for the query, we may do the region query first. So we just find all images consist of green rectangle and a red circle and a blue polygon. And then we identify the location of these objects and try to uh, find the uh, find the intersection of all these results. If an image consists of all three kinds of objects and the spatial location meets some criteria, we may finally return this image as the final result. So the characteristic of the VisualSEEK system is that they propose automatic extraction of local regions and features, and they enable query by both feature and spatial information, and they also propose some novel features and compressed data for compressed data. And then they develop technology for fast indexing and retrieval. And they also develop highly functional user tool. So you can see that this is a quite comprehensive uh, content-based image retrieval system. So you can realize why this paper is so typical in early times. So here's the system overview. So the user may give a query through the VisualSEEK query tool, or query by text, or just give the system give me more query. Okay, and then through the World Wide Web, we can send the query to the query server, and at the query server, the feature extract from the database or some metadata may be compared with the feature from the query images, so that the most similar images can be determined, and then all the similar images can be sent back to the user side, and from the user client side, the retrieved images may be represented as thumbnail or keyframes, and then present to the user. So now we are talking about the features that would be extracted from the images. In this paper, they propose the feature called color sets. Okay, so here, given an image pixel, it would be represented with RGB. Okay, red, green, and blue. And then first, according to the color space uh, concept we have mentioned before, RGB color space may not be so suitable to describe image as our human perception is more similar to HSV color space. So first, they just transform the RGB color space to HSV color space, and then they do some quantization. So QCM is a quantizer that partitions the color space into M subspace. So you can imagine that the HSV color space is divided into M subspaces. And then if some pixels colors falling into one of the subspace, then this subspace is labeled as 1. Otherwise, this subspace is labeled as 0. So that finally we can get a feature called color set. A color set is a binary vector in BCM, in this binary space, which corresponding to a selection of color M. So in words, in words, the binary vector showing which subspace uh, has the pixel. Okay, or on the other hand, I can say that um, it's a binary vector indicating if some pixels color falling in the first subspace, then the first subspace will be labeled as 1. And if there is no pixel color falling into the second subspace, then the second dimension will be labeled as 0. So this will be a binary vector showing 1, 0, 0, 1, 1, like something like this kinds of binary vector. And for this binary vector, that means the color falling into the first subspace and the fourth subspace. So this is the so-called color set. So here is the detailed parameters. So the transformation is they transform the RGB color space to HSV color space. And for the quantization, they quantize HSV color space to two hue region, two saturation region, and two value region. So there are totally 8 subspace. So the BCM is an 8-dimensional binary space. So for a color set, that would be like this: 100101000. That corresponds to the selection of 3 color. Okay, the first one, the fourth one, and the sixth one from the quantized HSV color space. And you can say that the color set feature is kind of simplified version of color histogram, because in color histogram we don't represent color histogram by binary vector. We represent how many pixels belong to this subspace. But in color set, if some pixel belong to this color space, we just label it as 1. Otherwise, label it as 0. So we can see, we can view the color set feature is actually a simplified version color histogram. So color set provide a compact alternative to color histogram for representing color information. And if you simplify color histogram, you may have information loss. But that would be a compromise between retrieval accuracy and retrieval efficiency. If we represent images by binary vectors, then we can use simple operation to calculate the similarity between different images. And 20 years ago, at that time, the computer system is not so powerful. So if you have many images, you may put more emphasis on retrieval efficiency rather than retrieval accuracy, okay, at that time. So the color set features was proposed because from the conjecture that salient region have not more than a few equally prominent colors. That says in an images, we can conjecture that only few regions are very salient, and the salient region just have a few distinct colors. Okay, they don't have so many colors. They just have a few distinct colors. So that they propose the color set feature. So here's the concept. So they transform the RGB color space to HSV color space. And here, they actually, in their paper, they actually quantize hues channel into 18 regions, saturation channel into 3 regions, and the value channel into 3 regions. And they also define 4 gray regions. So actually, they have 166 colors in total. So basically, they construct a 166 dimensional binary vector. Color set is not only used to represent pixels, but also used to detect color region. So they propose the color set propagation process to extract color regions. The process statistics, they first select some prominent color set, and then they projection onto the image, projection the color onto the image, and then they do some thresholding and labeling. And the so-called projection process is given image I and the color set C, that K be the index of the color at the image point. Then generate image BXY by setting all the BXY image points as the CK. We can see the example images here. So given the color set, we can rewrite all pixels whose color are quantized into this color set as the representative color according to this color set. So we can get a binary image like this, and then we can, because we have already rewrite all the pixels belonging to this region as the same color, and rewrite all the pixels as the same color. So we can clearly see several regions. So here's another example. So given these images, if we do back projection, that means all the pixels belonging to the grass, you can see that may be reset to exactly the same color. Okay, so that the grass region may be extract after some post-processing like thresholding and morphological operation. This region may be extract. Okay, and all the regions belonging to the zebra may also be extract. Okay, so for every images and from every region, we have the corresponding color set, and we can extract the center of this region, also the area of this region, and the width and the height of this region's bounding box. So this is all we have from an image. So in a word, to summary, for each image, we may have several regions, and for each region, we have the corresponding color set, the centroid of this region, the area of this region, and the width and the height of this region. And based on this information, we can do region-based query in the following. So to calculate the similarity between different images, we have several ways to calculate the color similarity between different images. Okay, so here are several techniques to calculate the color similarity. If we represent images by HSV color space, we can calculate similarity between any two color MI and MJ like this. MI and MJ is represented by HSV, and here is one way to calculate the similarity between these two colors. So we can see that it's basically the distance between value, distance between hue, and with linear weight by the saturation. So this is one way to calculate the similarity. And if we represent images by color histogram, then we can calculate the color histogram difference between them. Okay, so here we can see that this is the color histogram formulation. Okay, so we just do color quantization, and then accumulate the numbers of pixels belonging to a bin. So this is a color histogram. And although the mathematical formation looks a little bit different from what we have mentioned before, but actually the meaning is quite the same. So based on color histogram, we can calculate the histogram distance like this. Okay, this kind of formulation is called a Minkowski matrix. So we just calculate the distance between corresponding histogram bin, and then we take square r square, and after summation we take the r square root. Okay, but such Minkowski matrix may cause a problem. A dark red image may be equally dissimilar to a red image as to a blue image. But for our human perception, we may feel that the dark red image is more similar to red image, and it would be distinct from the blue image. But if you take the Minkowski form matrix, this will be a problem. So some technology has been proposed to handle this problem. That's called a quadratic distance. Okay, so it measures the weighted similarity between histogram. So the formulation is like this. If we just ignore the matrix A here, the HQ minus HT transpose times the HQ minus HT is exactly the same as the Minkowski matrix. But right now, we multiply a matrix A here. In matrix A, the entry Aij denote the similarity between colors with index I and j. That means when we calculate the histogram difference, we also consider the similarity between different colors. So since the histogram quadratic distance compute the cross similarity between colors, it's more computational expensive. However, it would be a more accurate way to measure the similarity between two color histograms. And here is an example. For example, if we only have three types of color, red, orange, and blue, and if we represent an image by a three-dimensional color histogram as the distribution of red, orange, and blue, and we may have the correlation matrix like this. Okay, so this matrix measure or this matrix represent the similarity between different color. So in the diagonal, we have the highest similarity between red and red, orange and orange, and between blue and blue. And between red and orange, the similarity would be 0.9. The similarity between red and blue may be 0. Okay, so we can have such a similarity matrix, and if we calculate the histogram quadratic distance, then we have the following result. So let's consider a pure red image that will be represent like 100, and a pure orange image that will be represent as 010. And the quadratic distance between x and y is 0.2. The Euclidean distance, or the Minkowski form distance, the second order Minkowski form distance between x and y is square 2. Okay, so square 2 is about equal to about 1.414. Okay, and we can see that um, for human perception, we feel that the red image is similar to orange image. Okay, so you can see that the distance between red image and orange image is smaller. But if we measure by Euclidean distance between x and y, and if there is another image called z, z is a pure blue image, that would be 001. Then the distance between x and z is also 1.414 if we take the distance, if we calculate the distance based on Euclidean distance. Okay, so this is the problem about this is the problem of the Euclidean distance. Okay, the distance between red and orange is equal to the distance between red and blue. And if we take the quadratic distance, we may more accurately measure the color similarity, more match with our human perception. So we can represent images by color histogram and calculate the Euclidean distance and the quadratic distance between them. We can also represent images by color set, and then we can calculate the color set. We can calculate the similarity between images based on quadratic distance or Euclidean distance. So here is the formulation for quadratic distance between two color sets, CQ and CT. So given the similarity measurement mentioned above, we can calculate the distance or the similarity between different images. And so given a query Q, that may consist of several images, CQ. The best match to the query image is the target image that consists of several regions where the distance between the regions in this image is the smallest one to the query image. So basically, given two images Q and topic and an image in the database, the image Q may consist of several regions. The images from the database may also consist of several regions. We just can calculate the similarity between any pair of the regions. So we calculate the similarity between this region and this region, this region and this region, and this region, and also this region, and also calculate the similarity between this one to this one, this one to this one, and so on. And the image T is selected as the return image if the distance between objects, between regions, is the smallest one. So this is the so-called color region matching. The color region matching is accomplished by performing several region query on the query colors on the query color sets color, taking the intersection of this list and minimize the sum of the attribute in the intersection list. So for the database image T1, that may have a region similar to a region in the query image. And then there may be another database image T2 that consists of another region that is quite similar to another region in the query image queue. So we may return several images, and then we just take the intersection as we mentioned before. Okay, so some images may consist of the red circle, and some image may consist of the green rectangle, and then we just take the intersection and finally return all. We just return the images that consists of all the red circle and the green rectangle and the blue polygons. So the mentioned above are all based on color information. And right now we talk about the spatial query. Okay, and there are two types of spatial query. The first one is the fixed query location, and that means we just try to find the images that have blue regions at the left part and a red region at the right part, and the location would be similar to this setting. And the spatial distance between regions is given by the Euclidean distance of centroid. So SQ and YQ is the query region, the location of the query region. XT and YT is the location of the centroid of the target region of the target region. So we can just compare uh, the spatial distance between two regions. And if uh, if an image consists of region that uh, whose location is close to our target, and then we can return this uh, image. And sometimes we may try to relax the criteria or the constraint of spatial query. So we just define some bounded query region. So user can specify bounds within which a target region is assigned to a spatial distance of 0. For example, we just assign all the right region located at the right path would be fine to our query. So all the right region located at the right path, the spatial distance to the target would be 0. Okay, so when the target region is outside the bound, we calculate by Euclidean distance. However, if the target region is inside the bound, then the spatial region is set as 0. And it is useful in many situations when users don't care about the exact position. So here is the formulation. If the centroid location is inside the user specified bound, then the spatial distance is 0. Otherwise, the spatial distance is calculated based on Euclidean distance. If you have many images in your database and each image has many regions, then there will be a problem that you calculate the spatial distance between all the region pairs. So we need more efficient way to index the location of each region. The way used here is the CRA tree. The centroid of the image region are indexed using a spatial CRA tree on their x and y values. And this spatial structure provide quick access to 2D data points. The idea is that this. So given the image plane, we can divide the image plane into 4 equal parts. And for each subpart, we may even divide these parts into 4 smaller equal parts. And according to the numbers of points, here a point corresponds to a centroid of an image region in the database. So according to the numbers of points inside each part, we would determine whether we will further divide each smaller part into even smaller parts. So here we can see that there are many centroids located around the central part. So the central part of this image plane may be divided into many small regions. And then given a query image, if there is a region centered at this point, then we can efficiently traverse the spatial CRA tree to identify the part it belongs to, and to check whether the the centroids also in this part has similar region in terms of color or other feature, whether other regions located around this region is similar to the query region. So the spatial CRA tree is an efficient index structure for us to quickly locate some specific region. And for spatial query, we sometimes not only for the location but also for the area or the region that is covered by the image region. So we also need to do the region spatial location. We also need to check the region spatial location because we may need to check whether some region is contained by other region, whether two regions are overlapped. Okay, so region spatial location are also indexed by their minimal bounding rectangle, and the minimal bounding rectangle of the region are indexed using an R tree. So R tree is a region tree. R tree provide a dynamic structure for indexing rectangle. So this structure was proposed many years ago, and the R structure consists of a hierarchy of overlapping spatial node, and is designed to visit only a small numbers of nodes in a spatial search. So if we assign a query not only the location of the query region, but also uh, we also try to find some regions that is overlap with this region. Then we can use the R tree to efficiently index, efficiently retrieve the overlapped region. So if you are interested in related techniques, please refer to the reference we will mention it at the end of the paper. In addition to color, location, we will also try to measure region similarity based on their area. Okay, so the size of region is also considered. So the area distance is quite simple. We just uh, minus the area of the query region by the area of the target region, and take absolute value. And for the spatial extent, we also calculate based on the width and height of the minimal bounding rectangle. So basically, this measurement is to calculate the similarity between aspect ratio. Sometimes the region may be like this, and sometimes the region may be like this. So in this case, the distance between width and height is larger. So that means the aspect ratio of these two regions are quite different. So the spatial extent is defined like this. We calculate the distance between width and then the distance between height, and then sum them together and take the square root. So this is the spatial extent distance. So we finally introduce all the similarity measure in terms of from different perspective. So now, how do we process a query? So given a query region, okay, we will calculate, we will extract its color set feature, its absolute location, its area, and its minimum bounding rectangle. And then, based on color set, we can calculate the color similarity between the query region and any target region. And we can also calculate the spatial distance. Okay, and here we may have several policy to define the criteria of spatial similarity. Okay, and also the area distance, the aspect ratio distance, and then do some linear combination. We finally get the integrated distance between the query region and a target region in the database. Okay, so we simply linearly combine all these different types of distance and then get the final integrated distance. So given a query, we will try to find a region that best match the query region Q. And the query region Q can be characterized by the the color set, the centroid of the region, the area, as well as the width and height. So we first compute the individual query for color, location, size, and spatial extent, and then we take the intersection of the region that match that individually match some criteria in terms of color, location, size, and spatial extent. Okay, and for the regions that match the color constraint, we may have some return images, and we may also have some return images that match with the location criteria. And finally, we take the intersection of them to find the final result. And if we have multiple query region, we just intersect the result of single region match. So we first get the region A result, then the region B result, and then the region C result, and then we take the intersection of all the results retrieved from different individual region query. And then finally, we check the spatial relationship between these multiple regions, whether the region B is at the depth of region A, whether the region C is at the right of region B. Okay, we can check that, and then finally we filter out the result that don't match with this criteria, and finally we get the final result. So about the location criteria, we may specify like this. For example, we can find a region that best match these multiple query regions, where we can get or we can perform the single region query and get the set of result as region A, and then do this, and then take the intersection. And finally, we just return the result that has the minimum distance, that has the minimum overall distance to the query image. So this is the final match result. Okay, so the query is processed by intersecting the result region list to obtain the list of candidate image, and the best match minimizes the weight sum of the region distance between the query and the target image. So how do we check the relative position between multiple regions? They propose two ways. The first way is they just convert relative location into 2D string like this. For example, from T0 to T7, there are 7 regions, and here are the location, the centroid of these 7 regions. And we can simply project the centroid to the horizontal axis as well as the vertical axis. And then taking the horizontal axis as the example, we can read this project result from the left to the right. Then from left to the right, we have region 0, then region 1, then region 2, then region 7, region 3, region 6, region 4, and region 5. So we can, based on this string-based representation, we know that region 0 is at the left part of region 6, for example. And we can also do the same thing by reading the projected result from the bottom to the top. So we can know how these 7 regions locate at the image plane. And then we can compare these two strings with other strings we extract from the database image. Okay, so we can compare like that. These kinds of string representation may be influenced by scale or rotation. So they also propose a scale invariant and a rotation invariant string representation. That is also quite simple. We don't project the centroid to the horizontal or the vertical axis. We project them onto the 2 diagonals. Okay, the 2 diagonals. And in this case, we also can realize how these 7 regions locate, and this string representation is invariant to scale and rotation, because no matter how you rotate the image, the relative position between this region may be maintained. So finally, we can use the such string representation to get more reliable result. Okay, so for each candidate image, the 2D string is generated from the identified region and is compared to the 2D string of the query image. And the final operation either validate the target images or reject it. So we check whether the target image fulfill the criteria we specify associated with the query image. After all the process mentioned above, we now can give a multi-region query to retrieve images that have similar regions with some special or layout. So for the evaluation, user can in this work they design an interface, and the user can sketch the region's position and specify positions on the query grid and assign their property such as color, size, and absolute location. And the user may also assign boundaries for location and size. And as you can see here, the interface allows user to specify several properties. So here is an example to do retrieval. So this is the query specification. So this user try to find images where the top part of the image is in red, and the layer would be an object in yellow that would be inside this region. So this is uh, the query images, and the return images would be like this. The top 3 image would be like this. So this is the first return images. We can see that this is a sunset. This is also a sunset, and this is similar to sunset image. So we can see that this is quite matched with our expectation. And if we just describe the image based on color histogram, then the top 3 return image would be like this. We can see that although the color distribution is similar to the query images, but the content may not be in our expectation, because there may be a hole, a tree, or sand, or sometimes fruit. Okay, so using this example, the VisualSEEK system more appropriately retrieve images of interest. Here is another example. User may specify several regions, like the light from top to bottom, that would be in light blue, tan, or green. Okay, and the top 3 return image would be like this. As we can expect, there may be some sky on the top, and then some building, and then the green region. So we can see that the top 2 return images quite match with our expectation. But if you retrieve only you retrieve only based on the color histogram, then the top 3 return image will be like this, and we can see that these 2 image may not match our expectation so well. Also, this one is also maybe acceptable. To do quantitative evaluation, the author synthesize an evaluation data set. Because we Okay, so they synthesize, they randomly, um, they randomly generate images, where images may consist of several geometric objects, and then they randomly do some operations on these geometric objects like rotation, scale, and put into different colors, and then randomly compose them together to generate a synthetic text image. And because the whole process is under control, so we have the ground truth about where the, for example, where the green rectangle is, where the red circle is. So given a multi-region query, we can quantitatively measure the distance between the query image and the database image, so that we can uh, obtain a quantitative evaluation value. So here is the evaluation value. We use precision and recall curve to show the performance. The Q1 is the region indexing and the distance computation strategy proposed in this paper. Q2 is they use the same query strategy on a region database that was generated automatically from the target image using color set bit projection. So the difference between Q1 and Q2 is in Q1 we already have perfect region segmentation result. In Q2 we use the color back projection method to do image region segmentation. So because automatic process may incur some errors, so you can expect that the performance of Q2 is lower than the performance of Q1. And if we just conduct CBIR based on color histogram, the result would be like Q3. So we can see that Q1 and Q2 is much better than Q3. Okay. So how about the performance of the color set? As we said before, color set is kind of simplified version color histogram. So what if we use color histogram rather than color set? So here we also use precision recall curve to show the performance variation. D1, the curve D1 is the performance of color histogram quadratic distance, and the D2 is the performance of color set quadratic distance. And we can see that these two curves are quite similar. That means the proposed color set feature works very well, work quite similar to the color histogram. However, the color set feature is simpler, and the execution time, the execution time of measuring similarity is much less than color histogram. So this is the superiority of color set feature. So here are more examples about the VisualSEEK query. So given this query, we get this result. So we can see that we expect there is a red rectangle on the top of the image, and we can retrieve the traffic sign. And we may conduct multiple region query, like the green rectangle on the top and the red rectangle on the bottom. So we can retrieve an image like this. There is a tree on the top and a red box on the bottom. And also we can specify, for example, 3 yellow circle, and then specify the relative position. Okay, and then we retrieve this. So here is there is a red flower here, and a yellow flower here, yellow flower here, and a yellow flower here. And we can also specify more complex multiple region query. So finally, we can retrieve something like this.